My name is Abdul Bari. I welcome you all to the session on engineering mechanics important topic from ACE Engineering Academy. The topic of today's class is going to be the concept of Newton's third law and the concept of free body diagram. Now, if you ask anyone regarding Newton's third law, they would think that they know it very easily. Newton's third law is a very commonly known law. But this Newton's third law's misconceptions lead to difficulty in drawing free body diagrams. Okay. Let us start first of all with the concept of Newton's third law. We are discussing Newton's third law. What is Newton's third law? Very probably they are going to answer that Newton's third law states that for every action there is equal and opposite reaction. The statement probably is going to be for every action there is an equal and opposite reaction. Fine then. Then if you ask them, okay, what is free body diagram? Probably they would answer that freeing a body from its particular constraints and then showing all the forces acting on the body. Over here, the more important word is forces acting on the body. Let us say, we take an example. Imagine you are having a horizontal surface. On this horizontal surface, you are having a block. This block, let us say, has some weight W. The block has a weight W. And if I ask you to draw a free body diagram of this particular block, there's horizontal surface and a block, no other force available right now. So if you draw the free body diagram of this block, the diagram, let us say, is something like this. You are having the block over here, a force W going down, which is called as a weight, fine. There's one more force, which is going upward, vertically upward. This force is originating from the surface. Let us say that force is originating from here. That force is going vertically upward. Let us say it is called as normal. Incidentally, over here, W and normal are also equal. In the case of a horizontal surface, W and normal are going to be equal unless there is no other force acting on this particular body. Fine. Now, if I ask you, or if you ask someone, who is action, who is reaction? Very probably, people are going to answer that this W over here happens to be action, and N over here happens to be a reaction. N happens to be a reaction. If W is action, N is reaction, it makes some sense over here because W and N are equal, W and N are opposite. They are also having same line of action. So it is sort of making some sense. But if you ask yourself that in a free body diagram, you are supposed to show forces only acting on the body. When you have said W is action over here, then W is action basically means it is action by body. It would probably mean W is action by body. And N is reaction basically means N is reaction on body. So now there's a conflict over here. The conflict is, in the free body diagram, when you're supposed to show forces only acting on the body, why are we over here showing a force acting by the body? Somewhere something has to be wrong. Either our concept of free body diagram is wrong, or our idea of who is action, who is reaction is wrong. Or very probably, the concept of Newton's third law itself, what we have thought of, is wrong. Let us recapitulate quickly what we have discussed. We have at the starting we have discussed regarding what is Newton's third law. General answer for Newton's third law was every action has equal and opposite reaction. But the problem is with this third law statement itself. Newton has never said that for every action there is equal and opposite reaction. What Newton said was, for every action by a body, there is an equal and opposite reaction on the body. So when I say for every action by a body, equal and opposite reaction on the body, it means I'm supposed to have two bodies in interaction. There must be two bodies in interaction, then only you can have action-reaction pair. Which implies action-reaction pair can never exist on a single body. I'm again repeating this thing. Please mark these words. Action-reaction pair can never exist on a single body. Action-reaction pair is supposed to exist between two bodies in interaction. If one body is getting the action, the other body is supposed to get the corresponding reaction. You can't have action and reaction both on a single body. This is what is Newton's third law. So till here, whatever free body diagram you have drawn is correct, if this is what you are drawing. But if you are thinking that W is action and N is reaction, that concept is straight away wrong. And because of this wrong concept, people find difficulty in drawing free body diagram. And this difficulty becomes more complicated when you go for advanced subject based on mechanics like strength of materials, like theory of machines, or in case of civil engineering, structural analysis, likewise any design-based subject. So therefore, you have to get the idea of Newton's third law correct first of all. Let us see what exactly is Newton's third law then. So Newton's third law says that for every action by a body, there is an equal and opposite reaction. There is an equal and opposite reaction. Equal and opposite reaction on the body. Fine. This is your Newton's third law. Now this implies, it gives some implied meanings. Let us look at those implied meanings. What is the implied meaning of this particular law? The implied meaning of this law is, first you have to understand over here, action and reaction can't exist on a single body. Can't exist on a single body. On a single body. Action and reaction can't exist on a single body. Then how do action and reaction appear? They should appear between two bodies in interaction. They should appear between two bodies in interaction. They act between two bodies in interaction. This is a very fundamental rule. Please try to understand this rule. Action-reaction pair act between two bodies in interaction. Second thing you have to understand over here is, action and reaction are supposed to have same nature and they should have same line of action. What do I mean by same nature? Let us look back at what we have drawn some time back. We have drawn over here W and N as two forces. Now W happens to be what kind of force? We say W happens to be a force called as gravitational force. And N happens to be what kind of force? N is something called as contact force. Now these two forces, they might be equal in magnitude. They are opposite in direction. All is fine till here. But their nature is not same. W is a gravitational force, which is by the virtue of, law of gravitation, and N is by the virtue of contact, right? So since these two forces are having two different natures, they can never be action-reaction pair. For two forces to be action-reaction pair, it is compulsory that those two forces should have same nature. So second point I'm mentioning over here, action and reaction must have same nature and same line of action. Same line of action. Action-reaction must have same nature and same line of action. So if action happens to be a gravitational force, automatically reaction must also be a gravitational force. If action happens to be a normal force, reaction must also be a normal force. That is very important. And they should have same line of action also. If the line of action of action force is this way, it should be exactly opposite in the same line of action. Fine. Let us try to understand one very important action-reaction pair. After having understood this concept of Newton's third law, let us try to understand a very important concept. In physics, you must have come across something called as law of gravitation. What does law of gravitation, this is also given by Newton only. What does law of gravitation say? Imagine that you are having two bodies. This is body B1, let us say. There is another body over here. This is body B2, let us say. Two bodies are there. These two bodies are having some centers. This is, let us say, center of body B1. This is center of body B2. Centers over here. Let us say these two bodies' center are separated by certain distance. The distance between this is, let us say, equal to r. It is having some mass m1. It is having some mass m2. Now, Newton has said that when two bodies having some masses m1 and m2 are separated by some distance r, they are going to create some mutual attraction between each other. This m1 is going to apply an attractive force on m2. Likewise, m2 is going to pull m1 as well. This attraction is known as gravitation. And let us say this attraction is acting along the line joining the centers m1 and m2. So let us say over here you are having a certain force. Over here you are having a certain force. Likewise, over here you are having a certain force. Now these two forces are supposed to be equal and they are supposed to be opposite. Fine. Let us say this is a gravitational force acting on second body by first body, and this is gravitational force acting on first body by second body. If you look at two forces, these two forces have same nature, same magnitude, opposite direction, same line of action. These two are forming over here. These two are forming over here. These two are forming over here an action-reaction pair. This is an action-reaction pair. And you're observing action-reaction pair is not acting on a single body. It is acting on a pair of bodies in interaction over here. Now, we also know from basic physics that the value of this F12 in magnitude is equal to F21 in magnitude, and it has to be equal to G into, let us say, M1 times M2 divided by R square. Very famous law, Newton's law of gravitation, very famous law. Now, I don't have to go into details of this law, but let us say, for the sake of enjoying this concept, we take M1 as Earth and we take M2 as some mass, some body. In that case, if we do so, let us say, we are having over here Earth. This is Earth, let us say. This over here is Earth for us. And on top of this, there's a person standing on the surface of Earth. There's a person standing over here. Let us say Earth is having some mass, me, and this person is having certain mass, small m, let us say. And for the sake of simplifying, let us also consider that the radius of Earth remains a constant, even though it is a variable. But let us say, for the sake of simplifying, we regard the radius of Earth as capital R. Now, we can apply the same concept that force on Earth by body is equal to force on body by Earth. So I can write over here, force on Earth by body in magnitude has to be equal to force on body by Earth in magnitude. It has to be equal to how much? G into mass of Earth into mass of body divided by R square. Divided by R square. Now, if come to think of it, if I keep changing that mass, this person, let us say I am standing, next you are standing, next different people are present over here. If I keep changing this value of mass m, this value m would change, but G is a constant, does not change. Mass of Earth does not change. And we have also assumed that radius of Earth remains a constant. This is also not changing. In such a case, this entire value over here is invariant for me. If this entire value is invariant for me, let me calculate this value. If I calculate this value approximately comes around 9.807, let us say, with the units meter per second square. I realize this is an acceleration, and we are going to name this acceleration as acceleration due to gravity on Earth's surface. So acceleration due to gravity on Earth's surface is 9.807 meter per second square, let us say. Now I realize that this entire force over here, would be equal to how much? This would be equal to how much? This would be equal to mass of that body multiplied to G. If it is mass of body multiplied to G, I realize this is basically that mass of body multiplied to g. That means this is equal to weight. This is equal to weight. Please make a note of this thing. Weight is not a single force. There are two forces which can be called as weight. Those two forces are what? Force on earth by body and force on body by earth. Both of them are actually weight. What do I mean by this thing? This earth over here is pulling this particular body down. Earth is pulling the body down with a force, let us say force on body by earth, which is equal to weight of the body, W. At the same time, this body is not keeping quiet. This body is also pulling earth in his capacity, whatever capacity he's having. In that capacity, he's also pulling earth upward. And this is, let us say, force on earth by body. That is also equal to weight of body. So if earth is, let us say this marker over here, this pen over here, if earth is pulling down this particular pen with 1 Newton, let us say its weight is 1 Newton, if earth is pulling down with 1 Newton, he is also pulling earth upward with 1 Newton. He is also pulling earth with 1 Newton. But that 1 Newton acting on earth is insignificant because earth is so huge, earth's mass is so huge that this force, that is 1 Newton acting on earth, is very insignificant. Likewise, any body's weight is acting on the body. At the same time, the same weight is also acting on the earth in the upward direction. But the only thing is that force acting on earth is insignificant. Even though it is existing, it is insignificant. That is why we don't bother showing it every time. Now please realize, W and normal you were thinking was action-reaction pair. That is wrong. If you are thinking so. What is actually action-reaction pair over here? W and W is action-reaction pair. Equal, opposite, between two interacting bodies, same nature, same line of action. Everything has been satisfied over here. Equal, opposite is satisfied. Between two bodies is satisfied. And same nature. If W is gravitational, this is also a gravitational force. And of course, same line of action also. Right? So this is what the concept of Newton's third law along with the concept of law of gravitation is. If you have understood till here, let us move further and draw the free body diagram of the same case we have seen some time back. We have said that we are having a block. That block is resting on a horizontal surface. And we wish to draw the free body diagram. The free body diagram is the simplest case. This is the simplest case we are having. But we want to identify who is action-reaction over here. In doing so, I would suggest, let us say, draw the block over here. Draw the surface which it is in contact below. And always is a universal body present, which is Earth. Draw it over here. So this is a block, surface, Earth. Three things over here. Let us start first of all. The first thing I'm showing over here, is W. Who applied this force W? Ask yourself this question. Who applied this force W? Please understand, body does not have any capacity to apply its weight on itself. When I'm showing this W, it is a force applied by Earth on the body. So this W over here is by Earth on the body. So let us say force on body by Earth. Force on body by Earth. At the very same time, what happens in the same line of action, you are supposed to show a force over here. Same W. If this W is, let us say, 10 Newton, this is also 10 Newton. 10 Newton over here. And this over here is force on Earth by body. Who is action-reaction pair? This and this is action-reaction pair. W and W is action-reaction pair. Next thing, the moment this body is in contact with the surface below, let us say this body is in contact with the surface. He is pushing the surface and the surface is pushing him back. Another action-reaction pair has been developed. This action-reaction pair we are going to call as normal. We'll discuss why it is called as normal. Let us say this is N over here, normal. He has applied this thing. So if I ask you who has applied on whom, you can say this is force on the surface by the body. On the surface by the body. Now, the moment he applies a normal over here, he will reply back with a normal over here. He will reply back with a normal over here. What force is this? This is a force acting on the body by the surface. Again, who is action-reaction pair? This normal and this normal is action-reaction pair. W and normal is not an action-reaction pair. W and W is action-reaction pair. Normal and normal is action-reaction pair. I can't emphasize anymore, but you have to understand this thing, that action-reaction pair can never act on a single body. It requires a pair of interacting bodies to create an action-reaction pair. Are you following this thing? Moving further, there is a very commonly asked interview question over here, that when you stand on a weighing machine, what does a weighing machine measure? Let us say you're standing on a weighing machine. Okay. People have a misconception when they ask you what is your weight. They answer you in kg. That is technically wrong, because weight is a force, kg is mass. Weight has to be in Newton, is it not? So when you stand on a weighing machine, what does a weighing machine measure? Let us say this is you and this over here is a weighing machine. Over here is a weighing machine you're standing. If you think about it, what is a weighing machine able to measure? What is a weighing machine able to measure? The only thing weighing machine can measure is normal. So when you stand on a weighing machine, what weighing machine measures actually is not your mass. It is not even your weight. It is actually measuring normal. This normal incidentally is equal to weight. Then inside the weighing machine, some calibration is being done, and that force is being converted into equivalent mass, and then you get the answer in terms of kgs. I hope you are following this thing. So when you stand on a weighing machine, it does not measure your mass, neither does it measure your weight. All it measures is a normal force, because the force acting on him is not the weight of the body, it is the normal acted by that particular body. Moving further, if you have understood till here, let us try to create one question. This is an interesting one. Imagine that you are having a surface over here. You are having a block over here. Let us say this block's weight is equal to W1. Over this block, you are having another block. The weight of this block is W2. Over here, you are having another block. Let us say weight of this block is W3. 3 blocks are present over here, right? If I ask you, draw the free body diagram of this entire system, okay? Then how would the free body diagram look like? Let us say this is a universal body for us, which is Earth. We generally don't show Earth because every force acting on Earth is insignificant from our perspective, right? That's why we don't show forces acting on Earth. Anyway, still, for the sake of establishing the concepts, let us respect the presence of Earth every time. This is Earth. This is the surface you are having. This is the block W1 you are having. This is a block W2 you are having. This is a block W3 you are having. So 3 blocks. Free body diagram basically means you are supposed to free the body or isolate the body from the system. Disassemble every body in the system. Show the bodies in the same orientation. Now let us start drawing. First thing first. The force acting over here on this body is equal to W3, let us say. Question is, who has applied this W3? If you are even watching this as a recorded video, please try to answer this thing. Who has applied this W3? It is Earth who has applied. The moment Earth applies, then there is going to be a reaction on Earth. This body is going to reply with W3. This is an action-reaction pair. Next thing, if you are thinking that on this body, W2 is acting, you are right. W2 is acting. And you are thinking W3 is also acting on this body, then you are wrong. W3 is not acting on this body. W2 is acting is perfectly correct. Why? Because who applied this W2? It is Earth. So Earth is getting back W2 over here. Till here everything is fine. But if you are thinking W3 is acting on this body, that is wrong. Because what this body can apply on this surface is a normal. It is a normal. So let us say on this body, I'm having some normal over here, N1. W3 is not applying its weight on the surface below. W3 can only apply a normal force on the surface below. It has applied this normal. The moment he applies this normal, there has to be an equal and opposite force. There has to be N1 back over here. Who is action-reaction pair? N1 and N1 is action-reaction pair. Again, I'm repeating this because this is where people have a lot of difficulty in understanding. Please understand that this body cannot apply its weight on the surface below. What it applies is actually a normal force. Incidentally, that normal might be equal to weight. That's a different issue. Incidentally, the normal is equal to W3. That's a different issue. But technically speaking, if you are saying that it is applying its weight, that is completely wrong. And that mistake will make you do many blunders later on in different subjects. So please understand, he does not have a capacity to apply weight on himself. How is he going to apply it on the other body? He does not have a capacity to apply his own weight on himself. It is Earth who is applying W3 on him. How can he apply his own weight on some other body? What he applies is actually normal. Moving further, this body is going to apply, let us say, some normal N2 over here. He is going to get a reply over here N2. And on this body, you are going to have, one moment please. This body, Earth is applying a force W1, let us say, and getting back a reply W1. W3 action reaction, W2 action reaction, W1 action reaction, N1 action reaction, N2 action reaction, likewise N3 action reaction. This is the actual free body diagram. And I hope you are all following this free body diagram, because if you understand these very simple things, very elementary things, then later on drawing free body diagram will be enjoyable for you and eventually easy also for you. I have seen people, they have finished engineering completely, both mechanical and civil, and still they are having difficulty to the point that they are afraid of drawing free body diagrams. Mind you, I'm using the word afraid. They're afraid of drawing free body diagrams. You see, most of the questions in mechanics and mechanics-based subjects are, one part of it is drawing the free body and the other part of it is to write equations. Writing equation is not a big deal. Writing equation is rather easy compared to drawing free body diagram sometimes. Because once you get the idea of free body diagram completely, equation is just interpretation of free body diagram in mathematical notations. So you see the diagram, you interpret it in mathematical notations, you get the equations. That is easy. But this part of drawing free body diagram, I hope it will be easier for you from here onwards. So this is the actual free body diagram supposed to be when you are having multiple bodies over here. Now the question over here, why is it called as normal? Why is this contact force called as normal? And regarding normal, you should know some fundamentals. Okay, what exactly is normal? Normal is a contact force. When two bodies are in contact, they are going to have a contact force with each other. Why do we use the word normal? The reason being, imagine there are two irregular shaped bodies in contact. Irregular shaped bodies in contact. This is body 1. This is body 2 in contact. Now the moment these two bodies are in contact, there is going to be a common tangent between them. Please don't mind my diagrams. Try to understand. This is a common tangent between them. This, let us say, is common tangent between the two bodies. The interaction between these two bodies is going to be perpendicular to the common tangent at the point of contact. This is a point of contact, perpendicular to common tangent, you are going to have interaction. That means this force over here is normal, you can say, or let us say it is an action, it is a force acting on body 2 by body 1. And this force is a contact force again, acting on body 1 by body 2. Action-reaction pair, of course. Now, if you are looking at this thing, these two forces are contact forces which are perpendicular to common tangent. In mathematics, the line or an arrow drawn perpendicular to common tangent is normal. That is why we use the word normal over here. So regarding normal, please remember this thing. Normal is a contact force. It is a contact force and it is supposed to be perpendicular to common tangent. Common tangent. Perpendicular to common tangent, this itself has a nickname, normal. Right. So drawing normal is quite easy for you, I hope. Moving further, let me get back over here. Let me make an interesting statement over here. Look at this thing. Look at this diagram. Imagine you are looking only at W3's free body diagram. Okay. You are looking at only W3's free body diagram. If you look at only W3's free body diagram, you are going to get something like this. This is W3. You are having W3 down over here. You are having normal N1 up over here. Normal N1 up over here. Okay. So you are having these two forces, fine. But what if you are observing over here W3 and W2, both of their combined free body diagram? Listen carefully. Okay. I'm saying, what if you are looking at W2 and W3's combined free body diagram? So let us say what you are looking at over here. What you are looking at over here is this free body diagram. If you are looking at this thing, imagine. If you are looking at this thing, then let me ask you something. In this entire free body diagram, is there any force whose action as well as reaction is present inside the free body? My question to you is there any force whose action as well as reaction is present inside that particular free body? The answer is yes. You are finding N1's action as well as reaction present within the free body. I'm looking only at this thing. Rest everything is blank for you, please. So if you look at only this part, you are finding N1 and N1's action as well as reaction. In such a case, you can say N1 has become something like an internal force. Internal force. And when it becomes an internal force, it nullifies itself. That means you don't have to show N1 and N1 anymore. So within a free body diagram, if action as well as reaction is present, its effect gets nullified. Because let us say upward direction is positive, downward direction is negative. I'm having same value upward, same value downward. Both of them are getting nullified. This will sometimes help you solve some critical questions. Fine. So whenever you are finding action as well as reaction within the system, then for that particular system, it has become an internal force. In such a case, its effect gets nullified. Its effect is getting nullified. Moving further, let me ask you one question over here. Let me ask you one question. This is a good one. The question goes something like this. Imagine that you are having a weighing machine. This, let us say, is a weighing machine. Imagine you are having some weighing machine. On top of this weighing machine, you are having some container. This weighing machine, you are having some container. This container is filled with some liquid. Let us say water. For the sake of understanding, let us say it is water. Let's say it is given to you that container plus water is equal to some 300 Newton. Weight of container plus water is equal to 300 Newton, let us say. Now, what I'm doing is, I'm taking a rope. To this rope, I'm connecting a body. A small body, let us say a block is there. I have connected. And I have submerged this inside water. Such that water is not spilling out. Water is still present over here. Water is still present over here. It is not getting spilled out. Let us say it is given to you that weight of body is equal to, let us say, some 120 Newton. And since body and fluid are interacting with each other, there has to be a force, which you study in fluid mechanics. It is called as force of buoyancy or buoyant force. Let us say buoyant force over here is equal to 75 Newton. Example sake. Let us take these numbers. 300, I have mentioned 300, right? Yeah, 300 is the weight of container plus water. Weight of body is equal to 120 Newton and force of buoyancy is equal to 75 Newton. My question to you over here is, what is the reading on weighing machine? What is the reading on weighing machine? So weighing machine is reading how much? Now first thing first, all of you should recall that weighing machine is not going to measure mass or weight. It actually measures normal. So basically you have to identify what is a normal being read by weighing machine over here. This is a question. Okay? Think over it. How would you solve this question? How would you solve this question? I have given you numbers, 300. Let us say, I forgot the numbers now. 120 and 75. 300, 120 and 75. Let us say you are hanging this over here using some support. Of course, you have to hang it using some support. Otherwise, it is either supposed to submerge down, or if W equal to FB, it can be still at some intermediate position. Let us see how to solve this thing. First of all, I am disassembling the entire system. I have over here weighing machine. Let us say this portion over here is container plus water. Let me mention, this is my weighing machine. This is container plus water. This is a random body I'm having. This is a body I'm having. Earth is always present. Now I'm going to stop showing Earth. You have to imagine that Earth is always present, right? First thing first, Earth is going to pull this body down with how much force? We have mentioned 120 Newton as its weight. Earth has pulled. This is an action done by Earth. He is also pulling back Earth. He is also pulling back Earth upward. Next thing, Earth is going to pull this body down with how much force? Earth is going to pull this down with a force of, let us say, 300 Newton. It's also pulling Earth upward with 300 Newton. But mind you, 120 Newton, 300 Newton are not going to make any effect on Earth. That is why we don't even bother showing that on Earth. Next thing, this container plus water and this weighing machine are having an interaction with each other. You see, they are connected to each other. Since they are connected to each other, there is going to be a normal action-reaction pair over here. Let us say we call this as N, we call this as N, action-reaction pair over here. Next thing, is the body in interaction with the weighing machine? The answer is no. By the look of this particular diagram, you are not finding body having any interaction with the weighing machine. Body, of course, is having interaction with the fluid. But body has no interaction whatsoever with weighing machine. Okay? So you're not having any interaction between body and weighing machine over here. What next? Body and the fluid is having an interaction. What is happening? This is interesting because this is going to, suddenly create some kind of new concept in you probably. What is happening? The moment this body is in contact with the fluid is trying to push this body upward by the virtue of hydrostatic forces, net hydrostatic force, which is ultimately a buoyancy force. Let us say force of buoyancy. Force of buoyancy. The moment the body is pushing, the fluid is pushing the body upward with force of buoyancy, let us say equal to 75, there has to be a reaction to this thing. Every action has to be coupled with a reaction between two bodies interaction. So that means this body is going to push the fluid down with an equal force over here, 75 Newton. This might be new to many of you, but please try to digest this thing. Force of buoyancy is not going to act only on the body, it is also going to act on the fluid. If the fluid pushes the body up, the body is supposed to push the fluid down with the same magnitude. Again, action and reaction because they are between two bodies in interaction. Fine. And furthermore, because there's a rope tied to this thing, I'm supposed to have one more force over here, let us say tensile force. I'm supposed to have one more force upward on that body, which is tensile force. What is tension and all? Most probably you must be knowing this thing. Right now I can't discuss those concepts. Let us save that concept for a different day. Let us say you understand what is tension. Now, my question is, what is the reading on weighing machine? The reading on weighing machine is normal and normal alone. I have to identify how much is normal. To identify how much is normal, I am going to look at this particular body's equation. I can write over here by the virtue of equilibrium, summation of force in y-axis is equal to 0. I can write summation of force in y-axis equal to 0 for this particular case. If I write that, what am I going to get? I'm going to get upward force is normal. Downward forces, I'm having two downward forces over here, minus 75 and minus 300 has to be equal to 0, which implies the normal is equal to how much? 375 Newton. The normal over here is equal to 375 Newton. And this is the reading on the weighing machine. The weighing machine's reading is going to be equal to how much? 375 Newton. I hope this is clear to all of you. Now, likewise, if I ask you in the very same question, if I ask you, what is the tension in the cable? There's a cable connecting over here, is it not? You're finding a cable connecting this body with the surface below or the ceiling over here. What is the tension in that particular cable? If I ask you, what is the tension in the rope or the cable, you can apply same thing. You can say, for this summation of force in y-axis has to be equal to 0. Summation of force in y-axis equal to 0 would give you what? It would say upward forces are, let us say, 75 and the tension. Downward force is 120 minus 120 is equal to 0. It is equal to 0. So from here you can say tension is equal to how much? 120 minus 75, let us say it is equal to 45 Newton. So tension is equal to 45 Newton. So right now the tension in the cable is 45 Newton. You can also call this tension over here as apparent weight. This is what appears to you as the weight. Imagine it is not attached to a ceiling, rather your hand is holding over here. It is your hand which is holding this particular rope and this mass attached over here. In such a case, its actual weight is equal to how much? 120. But what is your hand sensing right now? Your hand is not sensing 120, your hand is only sensing 45. It appears to you as if its weight is 45, even though its weight is 120. That's why you can also call this particular 45 Newton as apparent weight. This gives a concept of apparent weight. And we have many more concepts of apparent weight, even in the concept of, you can say, D'Alembert's principle. You'll come across apparent weights over there. So this is regarding the concept of Newton's third law, basics of Newton's third law, and the concept of free body diagram. I hope this session was helpful for you. The ultimate gist of this entire session is to remove that misconception of action and reaction pair. Most people I have seen have thought till now probably as action and reaction can act in a single body, whereas it is not possible. Action and reaction, remember, is supposed to act between two interacting bodies. And action and reaction should have same nature. That is also very important. Thank you. My name is Abdul Bari, and I hope this entire session was helpful for you. Thank you again on behalf of ACE Engineering Academy.